Hello everyone. Welcome back to Learning at 11th hour. Today we are going to continue with the maximum power transfer theorem and we are going to look at the third case. In this case, we are going to have a load impedance with a variable resistance, but the reactance is going to be fixed. So let us first find out what the current through this circuit is going to be. So say I have I flowing through this circuit, then what is the value of current that is going to flow through the circuit? So I is going to be given by the voltage divided by the impedance of the circuit. Here we have two kinds of impedance. One is the source impedance ZS, the other is going to be the load impedance ZL. So we'll have ZS plus ZL. Now we can expand this and write it as V divided by RS plus JXS plus RL plus JXL. Now we can take the real and the imaginary parts separately and rewrite it as V divided by RS plus RL plus J times of XS plus XL. So here S stands for the source and L here means the load. So now what is the expression for power? So power is going to be I square into RL. In fact, I'll say magnitude of I square into RL. So what is the magnitude of I? So if I take the magnitude of this value, what would I get? What I would get here is it would be V divided by what's the magnitude of a complex number? It is going to be whole root of RS plus RL the whole square plus XS plus XL the whole square. So this is the value of magnitude of I. Magnitude of I. So then what is the power now? Power is going to be the square of this value into RL. So what I get here is V square into RL divided by this entire parameter. So since I'm doing a square, the square root and the square goes away and what remains is R square plus RL the whole square plus XS plus XL the whole square. So this is what we are left with. Now we need to find out the condition for maximum power transfer. So to do that, we see that the variable parameter over here is just the resistance and not the reactance. Reactance is fixed. So we need to find the conditions based on the variable resistance. So we are going to differentiate the power with respect to the load resistance and then equate it to 0. Now on performing this differentiation, what do we get? So we are going to get this value V square RS plus RL the whole square plus XS plus XL the whole square, because we've differentiated this now, keeping this constant, then minus 2 times RL RS plus RL divided by RS plus RL the whole square plus XS plus XL the whole square and then the whole square equated to 0. Now, there are two conditions that arise over here. So, when we equate this to 0, we get RL to be equal to RS square plus XS plus XL the whole square, the whole root. So, this is basically the condition that we get. But from this, we can divide this into two subdivisions. The first case is where my source is going to be purely resistive. So, if my source is purely resistive, in that case, I can say that the value of the source reactance is going to be 0, which means this term will be 0. So, what will my XS be? XS is going to be 0, and therefore RL will become RS square plus XL square the whole root. On the other hand, the second case is where my load is going to be purely resistive. So if my load is going to be purely resistive, it means that there is not going to be any load reactance term. So XL is going to be 0. So if this parameter becomes 0, what I'm going to be left out with is RL is equal to the whole root of RS square plus XS square. And this term is nothing but the magnitude of the source impedance. So the second condition says that if the load is purely resistive, then the load resistance should be equal to the source impedance. And if the condition is that the source is purely resistive, then the load resistance should be equal to root over of RS square plus XL square the whole root. Let us now move on to the last case of maximum power transfer theorem. The fourth case says that the load impedance is going to be having a fixed angle and only the magnitude of that load impedance is going to change. So here we know that the impedance is going to be made up of both resistive as well as reactive components. So if I have the load impedance ZL, it is going to be made up of RL as well as XL. So this is the complex representation of ZL. We can represent it also in the polar form, and in that case this would be written as magnitude of ZL angle, I'll call it as angle phi. So this is the complex number representation of the load impedance, and this is the representation in the polar form. Now here it is said that the magnitude of the load impedance is variable, but the angle does not change. The angle is fixed. If that is the case, then what is the condition for maximum power transfer theorem? So this is what we are going to find out. Here, this phi is said to be the load angle. Now, we can expand this and write it as ZL is equal to ZL cos phi plus J times ZL sin phi. This is another way of representing the complex number. In this case, what would the power be? So the power would be given as V square ZL cos phi divided by RS plus ZL cos phi the whole square plus XS plus ZL sin phi the whole square. So what does this mean? This means that the cos component is the real part and the sine component is the imaginary part, meaning this is going to represent the resistance and this part is going to represent the reactance part of the load. So taking the cos component, which is a real part, and our s, which is the real part of the source together, we have the real components here and the imaginary part over here. So this is going to be I square. V square divided by this denominator is I square, and we have the load resistance as ZL cos phi, which is the real part of ZL, right? Now we can see that the magnitude of the load impedance is variable, which means I have to differentiate this with respect to the magnitude of the load impedance. So dp by dzl, and that has to be equated to 0. So when we do this, what we get here is we get the condition magnitude of ZL should be equal to the magnitude of ZS, meaning that the load impedance should be equal to the source impedance. So this is the case when the load impedance is having a variable magnitude with a fixed angle. So let us summarize the four conditions of maximum power transfer theorem. Here, the first case is where the circuit is going to be purely resistive and the load is a variable resistive load. So it's a purely resistive circuit. In that case, the condition for maximum power transfer becomes the load resistance should be equal to the source resistance. The second case is when the load impedance is made up of variable resistance as well as variable reactance. So here we did differentiation two times. One was with respect to XL, the other was with respect to RL, and we obtained the conditions XL should be equal to minus XS and RL should be equal to RS. And the maximum power that is to be transferred, it boiled down to the same expression that we got over here, which was V square by 4 times of RL. The third case is where the load impedance is made up of variable resistance but a fixed reactance. So here we got the condition that RL should be equal to root over of RS square plus XS plus XL the whole square. From this, we concluded two conditions. The first one is when the source is purely resistive. In that case, the condition for RL was that XS term would not be there. So RL would be equal to root over RS square plus XL square. The second one is when the load is purely resistive. That means there won't be any reactance in the load. Only the resistance term would be there. So we would obtain the condition as Rs square plus Xs square, which was nothing but the magnitude of the source impedance. So this was the third case. The fourth case is when the load impedance was having a variable magnitude, but the load angle was fixed. In that case, the load impedance should be equal to the source impedance in magnitude. So these are the four conditions uh, for the four different cases in order to obtain maximum power at the load side from the source side. That's all with today's video. I hope the four cases of maximum power transfer was clear to you all. In the upcoming video, we'll discuss some problems related to maximum power transfer theorem. Thanks for watching. Please to subscribe to this channel. Bye bye.